Welcome, I'm Lisa Bobotta from Environment Park based in Turin, Italy. We are a technological park active in the field on environmental innovation and sustainability. Our mission is to provide solutions for processes and products driven by circular economy principles. I am a senior researcher within the plasma nanotech sector, and my duties are centered around research, development, and technology transfer of software treatment based on plasma technology for application in different industrial sectors, such as biomedical, textile, and automotive. For Textbook, I'm going to present Unit 4.2 on textile and clothing waste. If you're ready, I can start the presentation. I share the slide with you.
Within the unit, we are going to learn about the definition of textile waste and its classification into different types based on their source of generation, toxicity, disposal, and discarding. In particular, pre- and post-consumer as well as toxic waste will be presented. Two sections are dedicated to the wastewater and air pollution deriving from textile industry. Finally, in the last section, different sorting technologies are provided. Waste is a product or substance which is no longer suitable for its intended use. Whereas in natural ecosystem waste, oxygen, carbon dioxide, and dead organic matter is used as food or a reactant. Waste materials resulting from human activities are often highly resilient and take a long time to decompose. The European Union Waste Framework Directive, the umbrella directive that provides definition for many legislative documents concerning packaging waste and light vehicles or waste from electronic and electrical appliances, to name a few, defines waste as waste means any substance or object which the holder discards or intends or is required to discard. The definition and the general approach of the European Union legal framework does make a distinction whether waste is used for other purposes. Reuse, recycling, other recovery, for example, energy recovery, or disposed of. Regarding textile waste, it can be defined as the textile bioproduct of the manufacturing of garments, fabrics, yarn, or fibers that are deemed unusable for its original purpose by the owner. Textile waste is produced through a number of streams, including the fiber, textile and clothing manufacturing industry, consumer as well as commercial and service industries. The world population has grown tremendously in the past few decades, and the same period also witnessed improvements in living standards in general. These two developments have augmented the consumption of textiles, which in turn increase textile production. The effect of the rising living standard can be seen in the fact that the worldwide consumption of textile is growing faster than the world population. The demand is expected to grow from around 30 million tons in 1980 to more than 130 million tons in 2025. For example, only around 2.8 million tons of textile were collected in Europe, whereas more than 4 million tons have largely disappeared in incinerators or landfill alongside with residual waste. Better collection, sorting, and management of textile waste is fundamental to ensure more use and recycling and preventing waste for being incinerated or landfilled. Textile and fashion waste can be classified into different types based on the source of generation, toxicity, disposal, and discarding. Pre-consumer and post-consumer waste, solid and soft waste, industrial textile waste, and toxic waste. Pre-consumer textile waste, according to Council for Textile Recycling, is the waste generated during production by processing fibers and the production of finished yarns and textile, technical textiles, non-woven, garment, and footwear, including offcuts, serge, shearings, reactive materials, and OB-grade garments. It's generated in textile supply chain prior to reaching the consumers. We can say that the pre-consumer material originates from the manufacturing of a product. Post-consumer material originates from its use. In fact, the post-consumer waste in textile is the waste generated at various levels after usage of the finished product by end consumer and could be any clothing or household articles which has been discarded or not in use for any reason, like being worn out, damaged, or outgrown. Waste can come from different mechanical processes in textile manufacturing, like spinning, weaving, knitting, and garment manufacturing. Spinning is a procedure of producing converting fiber materials in yarns. The fibers generated by the spinning industry have various other materials like seeds, twigs, dead insects, and dust. At each stage of spinning, there are different types of waste, like blowroom waste, carding waste, dropping, dryer waste, drum frame waste, and ring frame waste pinning. Spinning waste and their source are given in figure 3. Weaving is the second level after spinning. Here, the yarn from spinning section is sent further for doubling and twisting. Different types of wastage are residual yarns left on the scones after warping. In the warping clean section, it's not possible to empty all the cones, and there will always be a little amount of yarn left on the cones. Sizing waste is another kind of waste in a weaving factory, where in the weaver's bin section a new set of warp yarn is started. Hence, it's necessary to eliminate some portion of the yarns to ensure that properly sized yarns are wounded on the weaver's beam. Knotting waste. Knotting is done to ensure all the warp ends of two beams are available for attaching together. Knitting is a method by which a yarn or thread is converted into cloth or fabric or any other form. It's a complicated process, and any fault in the technique of loop creation results in wastage. Wastage may occur due to any reason, like yarn, fabric faults, lack of machine maintenance, sample production, problem of management, etc. Yarn faults are responsible for a maximum amount of wastage of yarn in knitting floor. There are various types of knit fabric faults, like barrenness, spirality, tink and thin place, holes, slaps, stink marks, stains, strips. Barrenness has horizontal stripes or streaks of uniform or uneven width visible in the fabric. It occurs when the yarn is at high tension, or there is a high level of variation in the thread count in the fabric. Garment manufacturing process is the end product converting semi-finished cloth into finished cloth. Wastage can occur at various stages. Inspection, sample for technological test. Cutting room. Wastage can be occurred from several sources, such as market utilization, cutting waste, roll surplus. Sewing room. Fabric strips for overlook machines. Threads remain, elastic tapes hands. Final inspection. Waste due to finishing ironing problems. Measurements faults, size mistakes. Another classification of waste in production is soft and hard waste. Soft waste is the waste in which fibers are relatively open structure. It can be reused at an early feed stage. It's generated from bloom to the ring frame and is usable for producing a low quality of yarn. Hard waste is the waste in which fibers are packed in a closed structure and need additional operation before using them with soft waste. These wastes are produced in ring frame, winding, weaving preparator, and during weaving operations. The majority of solid waste originates from other sources during operation like transportation, bale openings, services process, and housekeeping. The waste under this category includes tubes, pallets, cones, containers, drums, plastic wrap, corrugated cardboards, seams waste and paper waste, bags and shipping cartons. The common packaging materials used in the industry are plastic and paper-based. However, textile packaging contributes a significant amount of solid waste that damage the environment. The industry has responded in different ways to reduce the waste generation by promoting recycling, reuse, energy recovery, minimization, and using novel compostable polymers. This management of packaging waste is being adopted by larger retailers and brands in the effort to promote sustainability. Textile waste can be classified based on their toxicity. Hard to treat waste, hazardous or toxic waste, disperdible waste, high volume waste. Each of them has characteristics that demand a different pollution prevention and treatment approach. Hard to treat waste include those that are persistent, resist treatment, or interfere with the operation of waste treatment facilities. These include color, metals, phenols, certain surfactants, toxic organic compounds, pesticide, as well as phosphate. Hazardous waste is a subgroup of hard-to-treat waste. The impact on the environment of such a kind of waste is significant. They include metal, chlorinated solvents, non-degradable surfactants, and other non-biodegradable or volatile organic materials. These wastes originated often from no-process operation, such as machine cleaning. Prominent sources of disposable waste in textile waste processing are the following: print paste, lint, coating operation, solvent, waste stream from continuous dyeing, printing, and finishing. High volume waste are sometimes a problem for the textile processing units. These include the water from preparation and dyeing stage, alkaline waste from preparation, salt, cutting room waste, knitting oils, and warp size. These wastes sometimes can be reduced by recycle or reuse, as well as by process and equipment modifications. The textile industry is water consumption intensive. It's estimated that approximately 93 trillion liters of water is consumed yearly for the needs of the global textile industry. During manufacture, wet processes as the sizing, scoring, bleaching, dyeing, printing, and finishing use a considerable quantity of potable water and release high contaminated wastewater, high concentration of dyes and metals. Untreated effluents, which are directly discharged into water source, contaminate water stream and cause environmental problems and health uses for humans. The main environment parameters used to establish the wastewater pollutants are pH, temperature, chemical oxygen demand, biological oxygen demand, total suspended solids, and total dissolved solids, but also color and toxicity. Chemical oxygen demand is the overall oxygen concentration required for chemical oxidation of all the organic compounds contained in a wastewater sample. Biological oxygen demand is the concentration of oxygen consumed during the degradation of the organic compounds contained in a wastewater sample. It's based on the principle that if sufficient is the oxygen is available, aerobic biological decomposition, stabilization of organic waste by microorganisms will be continued until all waste is consumed. Total suspended solids and total dissolved solids measure the amount of particulate matter, teeny pieces of things, floating in the water. Total suspended solids is an important water quality parameter measure for wastewater treatment operation and environmental health. The particle, or solids, can be divided into two types by passing the water through a filter. The particles that are large enough to be held back by the filter are called total suspended solids, while the particles that pass through the filter are called total dissolved solids. Toxicities is a measurement of inhibition of biological processes caused by some substance present in water on the metabolism of the organism. Textile wastewater is characterized and composed made of color, non-biodegradable inorganic compounds, heavy metals, dyes, phenols, pesticides, surfactants, oils and fats, total suspended solids, chemical and biological oxygen demand, high levels of total dissolved solid, general deficiency in nutrients, high content of chlorine and salinity. Dyes are considered the most polluting elements since they have a great impact on the environment. They reduce oxygen in water bodies by blocking light, causing septic conditions. There are also mutagenic and carcinogenic agents for animals and humans, and toxic for plants as they inhibit photosynthesis. In the following two slides, a description of the wet processes generating wastewater is provided. While in figure 6, you can find a list of the characteristics of wastewater products. An overview of the textile wastewater treatments is provided in Module 6, Unit 1. Air pollution is the introduction of chemicals, particularly or biological material that cause harm or discomfort to humans or other living organisms, or damage the natural environment in the atmosphere. All textile manufacturing processes generating environmental pollution. Workers are exposed to the risk of breathing air polluted with dust and fly and contracting respiratory disease. Air pollutants produced by the textile industry include nitrous oxide and sulfur dioxide produced in the energy production stage. Volatile organic components produced in cotton, curing, drying, wastewater treatment, and chemical storage. Aniline vapors carry hydrogen sulfide, chlorine, and chlorine dioxide produced in dyeing and bleaching stages. Emission to air can be reduced by decreasing emission of organic solvents by changing to water-based products, using scrubbers to collect particulate matter, optimization of boiler operation to reduce the emission of nitrous and sulfur oxide, pre-screening chemicals using the material safety data sheet to ensure that chemicals are not toxic, identify sources of air pollution and quantifying emissions. I remind that post-consumer products are defined as any garment or household products that owner no longer need and decide to discard. There are several reasons for disposal of a garment, such as poor fit, low quality, worn out, board demand, the influence on the fast fashion industry on consumers that push them to dispose garments more often. The collection rate of textile waste in European Union are roughly 25%, with different differences across member states. A revision of the European Union Waste Framework Directive will oblige member states to collect this discarded textile separately by January 2025, but handling the immense volume of used clothing poses a challenge. In Europe, each country has a different such level of collection of end-of-life textile and their further treatment. Collection rates and the type of schemes to collect used textile vary significantly, both nationally and regionally. The different kinds of actors that can be involved in collection of used textile, as well as the textile waste collection model, were just presented in the previous unit 4.1. Sorting is the process that immediately follows the separate collection of the used textile and textile waste. In the sorting facilities, used textile are sorted to determine their further fate, reuse and for which market, recycling and which type of recycling, or landfill incineration. The sorting process can potentially be an important component of economic and environmental cost of the recycling process, as the better the textile are sorted into poor fraction, the bigger the change of selling the textile to a recycling facility where it can be recycled. There are three types of sorting: manual sorting, including specialized manual sorting, manual sorting with sophisticated handling techniques, and automated sorting. Manual sorting is not a technology as such, as it's performed by humans and usually done without technological aids, apart from conveyor belts and other feeding technologies. Manual sorting is the most widespread textile sorting approach used in Europe, with hundreds of sorting facilities sorting hundreds of thousands of tons of used textile. In France alone, for example, there were 54 sorting centers operating in 2018, sorting just under 100 60,000 tons of used textile. Many sorting is relatively expensive due to the labor cost, required experienced staff, and it's difficult to determine detailed fiber composition by hand. Only sorting by fiber type is possible. Following recipe of used textile at a sorting center, all non-textile waste is removed as the first part of the manual sorting process. At this phase, batches of textile that are contaminated by rainwater, mold, oil are also removed. This pre-filtering can be carried out by less skilled personnel in initial fitting phase. The next phase is to remove non-usable clothing and textile. Non-usable textile can be identified through damage such as rips and tears, miscoloring, missing components, etc. The reusable fraction is then passed on, typically via conveyor belts, to the most skilled sorting personnel to sort these into different categories, using their size and sense of touch. The number and type of categories the reusable textile are sorted into depends on the facility and the demand. Some facilities sort according to the style, type, color, season, target group and condition, and some have a sort by fabric or fiber composition. Manual sorting with sophisticated hidden techniques is also often referred to as semi-automated sorting. We refer to technological aids for assisting in the accurate sorting of fiber types and grade for reuse and recycle. For example, a scanner that is used by the manual sorters to assist them in determining material content. Advantages are: 1. The sorting of high-quality recycling can theoretically be carried out at the same time as the sorting for use, rather than requiring a new facility and processing stage. This can reduce space needs and costs. 2. Cost of machinery lower than the cost of labor. Example of a manual sorting with sophisticated hidden techniques is the Swiss company Textile that collects, sort, and recycles used textiles. Since 2008, the sorting personnel at the textile sorting plant in Stratford, Switzerland, have been using a headset that helps them classify every single textile by material, quality, and texture using their voice. This voice control sorting system is linked up to a computer that ensures that each piece of textile via a belt and air blowers finds its way to the correct storage container. This is done via a air blast that sends the textiles to a stillage or a large bag. The voice-operated pre-sorting system has been integrated to facilitate the sorting of textile into 60 categories. Automated sorting can efficiently and accurately sort most textile waste by color and fiber type, ready for input into high-quality mechanical or chemical recycling. Among the most promising technologies are near-infrared spectroscopy, as used by Fibersort in Netherlands, and radio frequency identification used by Textile in Sweden. Near-infrared spectroscopy is a technique sensitive to the molecular absorption of organic cosmetics in the near-infrared part of the spectrum, so types of fabric that can be recognized and sorted into uniform categories of fibers with specific composition, color, and/or structures. FiberSort is a European Interreg funded project where during a 3.5-year period, a demo plant for automated textile sorting using near-infrared spectroscopy was built and operated outside of Amsterdam. This system allowed the detections of garments from cotton, wool, viscose, polyester, acrylic, and nylon. The sorted fibers have a low level of contamination and can serve as monofiber inputs in the mechanical as well as chemical recycling for high-value textile to textile recyclers. Radio frequency identification is a method based on radio labels enabling information to be stored and recovered remotely. Radio frequency identification labels are implanted in the product. They generally contain an identifier which allows a certain amount of information on the product to be found thanks to an external database. Serial number, manufacturing date. Textile is a Swedish project that implements the use of a digital information carriers, radio frequency identification tags, integrated in garments to increase future traceability throughout the supply chain and facilitate substance sorting processes prior to recycling. At this point, I finished the presentation of the unit 4.2. I hope you enjoyed the lecture. In the next slides, you can find the list of references used to prepare the unit. Thank you very much for your attention.